So morning. Today the overview talk is about LIGO-India project. I'll try to give you a brief about the current status of the project and what our plans once we complete this project also, a little bit on that also. And I will touch upon the capacity building that we're doing, essentially in terms of system engineering and engineering capacity. There is a lot of work that is being done in building academic capacity, which is well known to you guys. I think there is a lot of workshops, courses being run by IUCAA as part of the academic build-up. There is a science white paper which is in the public domain or will be made available in the public domain with external funding to get academic partners involved. In this talk, I'll focus upon the lead institution activities, especially the system engineering activities and the capacity build-up and how it can help us to realize something beyond LIGO-India also in the long term if we want to contribute to gravitational-wave astronomy. Yeah, so let me start with this. So most of you would know, but just for completeness, LIGO-India project is a project that's funded under the Mega Science project. It is shared between the Department of Atomic Energy and Department of Science and Technology, both contributing half to the construction of the project. However, since LIGO-India is led by the Department of Atomic Energy, since most of the lead institutions are in DAE, it's kind of complementary to TMT in some sense. TMT is led by DST institutions, but DAE contributes its funds. So it's in that context. So we have a total sanction cost of around 2,600 crores for a period of 7 years. We received approval in April 2023, and we are supposed to complete the project by 2030. And so this is for the construction phase. We would have a new project for the O&M phase, which is operational and science run case, which will be a later part of this activity. So this is for the setting up the observatory and starting the engineering runs, or probably one science runs along with the LIGO US colleagues. Yeah. So currently, the LIGO-India project in the DPR is written as an advanced LIGO project, but halfway through, we were able to get sanction for modifying the civil and the vacuum to match what will be required for the A+ configuration of the detector. However, the main component for the A+, which is the squeezer, is not funded as part of this project, which I'll touch upon later. And the idea would be to get those extra sanction for that squeeze light source so that we can arrive in an A+ configuration in early 2030 or late 2030. With a sensitivity typically of 100 megaparsec, and so that we can start doing science with this detector. So this is what we intend to do, build the Indian detector and operate it as a kind of a LIGO gravitational network along with the two observatories which are currently running in the US, Hanford and Livingston. And the 4 lead institutions for the construction phase, DCSA, which is a DA institution which looks after acquisition, construction, and civil engineering. And this is what this is the institution that has done the acquisition of the site, the detailing of the civil, and the construction contract for the project. IPR is the institution which is responsible for the vacuum design, vacuum engineering, and procurement. And I'll touch upon the activities that we have done on the vacuum part. ARACAT is responsible for the detector in the sense of the optics and the laser system and the overall project management to some extent. Along with the other colleagues. And IUCAA, as you know, is the partner who's doing the data analysis, the data center and part, and also the overall scientific management of the project. So the main motivation for LIGO-India, most of you would know, but just to emphasize on this again, is the large triangulation baseline. 3 detectors with similar sensitivities will go a long way in being able to localize the gravitational-wave sources, enhancing the possibility to do gravitational astronomy with other follow-ups. And that is where LIGO-India becomes beneficial in the sense of the long baseline that we have with respect to the other 2 detectors, something like 36 milliseconds and 39 milliseconds. Yes, so this is a slide I borrowed from Professor Kipthorne's presentation to the ETG while we were going for a project approval. So you'll see the advantage of LIGO-India in terms of the blue versus the purple with the presence and the absence of LIGO-India. The slide many of you would have known, but it kind of emphasizes the advantage of why LIGO-India is crucial for source localization and for gravitational-wave astronomy per se. So to just give you an idea about where it's going to be, it's in Aundha. It's a site which is close to Hingoli. Hingoli is a small town in the south of Maharashtra, 65 kilometers from Nanded. And the LIGO-India site is around 13 kilometers from Hingoli. And Hingoli is a place which will be the base of operations in terms of the staffing quarters and other things. And Nanded will have a small guest house to facilitate people arriving, because Nanded is probably the only airport that may become operational. It was operational for some time, but currently it's not operational. That's what I understand. The other way to reach the site is to come to Aurangabad and drive down by road, and that is another way to reach there. So as part of the pre-project, the site acquisition is completed. That was one of the pre-steps for for approval of the project, because as you know, site acquisition is a tricky task in India, and we have been lucky enough, and with counsel from many senior colleagues, we were able to choose a site which was easily acquirable. And this site has been acquired purely by direct procurement, which prevents litigations and other issues in the future. And that's one risk that has been retired in terms of site acquisition, which allowed us to move forward with the main project funding. So this is some brief on the site. We have all the prerequisites for the approval, which was completed as part of the pre-project. We had to seek for environmental clearance, which was applied for and received. And recently it has been extended for 5 years to cover the duration of the construction. A geotechnical survey is completed to do the estimations, both for site leveling and the excavation costs and other planning for the civil infrastructure. Baseline seismic survey has been done. This is to get an idea about what the starting seismic noise was. The site was selected primarily because of the low seismic noise. It's comparable or slightly better than the Hanford site in the US. We also done a drone survey essentially to find out the construction and developmental activities on the site to have a baseline about the anthropogenic noise. There's a weather station currently operational, which acquires continuous data across the year in terms of temperature variations, humidity, and wind gusts. So these are some data analysis that's been done for the seismic survey. And as I said, our site has a low seismic noise, which we hope to leverage and build a detector that has a sensitivity similar to the LIGO detector, if not better than that. So as part of the pre-project activities, the civil design was developed. The DBR was reviewed by the LIGO labs to make sure we use lessons learned from the other two observatories, both during the construction and the operational phase. And these changes were incorporated to make sure that some of these issues that we faced during the operation of the LIGO observatories in the US can be mitigated to some extent. And that has been addressed in the contractual documents also. This is an artist rendering how the buildings look like. Unlike the US buildings, which are built using construction steel, ours will be concrete buildings. So there's a bit of difference in terms of the building residences, acoustic modeling, and other things that we need to do for this building as part of external funding. And is also part of the engineering activities of the EPC contract for the civil contract. To build up capacity for the vacuum part, the colleagues at IPR had done the vacuum prototyping effort. Apart from the two chambers, which are the BSC and the HAM chambers, which are repeated multiple times to accommodate the detector, which I'll show in the subsequent slides. One of the key elements was a cryo pump and a beam tube test bench, which gives people the expertise how to do fabrication, QA or quality assurance during the fabrication, ensure that they meet the technical specifications of the tender, and then finally do the installation and testing. So the beam tube dimensions are similar to what LIGO-India would be installing at the site, and the cryo pump is identical to what we will be using in the LIGO-India vacuum system also. So that gives you the required expertise developed within the country, so that they are less of a R&D effort during the construction phase of the project. Currently, the LI Vista facility, which is functional at IPR, has achieved something like 3 × 10⁻⁹ millibar. This is a slightly older slide. And you can get in touch with the subsystems lead, Vijay Bedaki at IPR, if you want to do some experiments on this facility. The other thing that has been done at the vacuum facility is to build the control systems, which is similar to what would be implemented for the LIGO-India observatory, which is based on Beckhoff. And the intent was to build identical systems, which would then translate to the observatory, so that people training on this are not surprised by new systems at the site. And this is similar or identical to what has been implemented to LIGO observatories. To a large extent, we have avoided reinventing things which have already been well established and proven in the LIGO labs. This was a prototype vacuum chambers I talked about. So this was prototyped early in the pre-project phase during the COVID, in fact. And these two chambers are available for pump down and other testing. And this is something that will be used as part of the training of expertise. Constructing these two chambers in the country retired one of the risks whether these can be fabricated within the country. So the Indian vendors were able to meet the specification in terms of dimensions. Since this was done during the COVID period, the acceptance was done at 10⁻⁷, but the rate of pump down was matched with the data for the rate of pump down for the chambers when they were accepted in the LIGO US, giving us an idea that they achieved the required leak tightness that is required for the LIGO lab. But to doubly ensure that, we are going to pump down this at a later time this year, as we have time once the tender part is completed, because the same team works on both these activities. So having done all these key activities, we were able to put together the required inputs for the EPC tender. The EPC tender is an engineering, procurement, and construction tender. When we wrote the DPR, the intent was to go by the conventional way of tendering, where we would have had a civil tender and a vacuum tender, where the designs will be ours and the vendor would be required for construction. But however, by the time our project got approved, the procedures and processes for large construction projects and large projects of Government of India had to go through EPC contract. It has a certain advantage in terms of including the engineering interface as part of the EPC tender, and that has been included here, so that the interface between civil and vacuum is something the engineering firm that is taking up the contract has to do, and that gives us an added handle on the manpower that we require to do that part. So the EPC tender, after all vetting internally and approvals were floated on the EPC tender CPP portal on April 16th. Initially, the due date was in July, but many of the prospective vendors wanted more time. This is a very critical construction and fabrication contract. The civil facility has to meet many first of its kinds requirements in the country in terms of acoustic noise, casting a single slab, which is pretty large in one pour, and also the beam tube level has to be line of sight, not the geodesic. So these things, and also the vacuum system had critical requirements in terms of hydrogen outgassing, contamination control. And given these criticalities, the vendors had approached multiple times for extensions. So currently, the bids are due in the next week, and we hope to have a couple of bids which we think would meet the requirement in terms of technical and pre-bid criteria. And if all things go well, we are hoping to have the EPC contract placed by later December part or early January, kicking off one of the main schedule drivers for this project, which is the construction of the observatory and the vacuum system. Once this contract is awarded, probably the largest risk to the project is retired to some extent, and we focus on the detector shipment, installation, and its commissioning efforts. So this is the optical configuration of the advanced LIGO detector, which is in the DPR. I'm not showing the A+ part simply because that's not funded at this point, though the vacuum and the civil part is funded. The EPC contract includes the construction for the 300 meter filter cavity construction, and also the vacuum beam tube for the filter cavity. However, the detector configuration does not include the squeezer and the squeezing arm. So that is something that I'll touch upon later. So given this optical layout, the initial focus is on the laser system, which is something that we want to start out earlier on and install and commission because it's a complex enough system. And the other critical items are the suspensions, building the quad, control systems training, and the optical layout for the whole system, which is what we are working on. I'll brief this a little bit later. So as part of the systems logistics, we have been having meetings to plan for this detector shipment. This is the in-kind contribution for the LIGO lab for the contract for this project as part of the contribution. We have this detector shipment and pathfinders essentially to learn the nuances of not only shipping the detector in terms of packaging and how to move components, critical components safely, but also the paperwork in terms of how to move components across countries in terms of shipping and shipping documentation, also customs and other kinds of efforts. So this is work in progress. Currently, NSF review for the shipment readiness is being prepared for. We're putting together documents for getting the plans reviewed, and this would happen in the later part of this year or the early part of next year. While the construction happens, we will be receiving this detector components like the PSL and some of the isolation systems. So we need a space to install and commission them. So as part of the pre-project, we built a clean facility at Arakat as part of the pre-project activity for this purpose. This has the required cleanliness, acoustic isolation, and clean ambient, similar to what the LVA would have at the observatory, so that we can do some part of the detector assembly and testing while the construction happens at the site. So this facility is known as the LIGO-India Testing and Training Facility, and this was inaugurated in December of last year by Chairman AEC, and now it is available to the project as part of the construction. So the testing and training facility consists of two parts, a small set of labs for the various activities like the metrology of the optics, the PSL setup, which I'll come to, and the fiber drawing facility and optics metrology, and a large high bay area, which is around 75 meter by 25 meter, which apart from housing the 10 meter would be the space in which we will receive the detector components when they arrive at Arakat in India in the initial part before the observatory is ready. And almost 1/3 of the detector we hope to receive and test in this facility before it goes to the site. The building at the site that we are asking earlier on is a staging and storage building. So the day the staging and storage building is ready for acceptance and for beneficial occupancy, subsequent detector shipments will directly go to the observatory, and we'll be doing the remaining activity of the detector testing and preparation at the site directly, so that we avoid this two-step process. So as I mentioned, the pre-stabilized laser is the initial focus. The subsystem team responsible for this had been working on the various components and the logistics of shipping. Initially, we are starting out with just the 35-watt preamplifier. The power amplifier has been replaced with the bought-out amplifier, so we're not worrying about this at this point. And probably initially we'll target the 35-watt as the configuration for the LIGO-India operation also. So this is how the system looks at Hanford. This is something similar what we need to build in the LIGO-India facility or the LIGO-India testing and training facility at Arakat before it is reinstalled at the observatory. Towards this, we have been preparing a PSL clean room. The tender for this is in progress. We'd had some issues with the new mechanism of procuring on the GEM where anybody and everybody quotes for it. So we have been taking some time to kind of meticulously reject people who are not capable of doing the contract. This is in the final phase of the technical evaluation. And we hope to have the tender issued and complete this construction by the time the PSL gets shipped in March, April of next year, which is the schedule that we're planning for. This essentially uses one of the clean room labs in the testing and training facility and builds in a lab kind of PSL room, which has the required safety and the cleanliness required for installing the system. Part of the input comes from the PSL reference lab at Hanover, and inputs from the LIGO lab in terms of what are required to meet the safety requirements and also to meet the technical requirements for the laser installation. The second Pathfinder shipment is the isolation systems. So one of the relatively simpler system is the HAM ISI, which is planned for shipping in the early part of the next year. And towards this, the preparation of the test benches on which they'll be installed and commissioned has been prepared, and they're ready for receiving the detector components. We're in the process of preparing, as I said, the shipment readiness review for the Pathfinder 2 also, along with the Pathfinder 1. These different subsystems which are doing this. One of the most critical expertise that we need to develop within the country is the drawing of the suspension fibers and building the quad, because this is what essentially achieves the required vibration isolation for the core optics and directly dictates the sensitivity of the detector, apart from other things like coatings. And this is a facility that we are fortunate to have a small project called GetGo under a DST-STFC funded with Glasgow University, and Glasgow University had contributed this expertise to LIGO also as part of this DST contribution. And along with them, we are building this fiber drawing facility at Arakat for the India project in the TNT facility. And this is targeted for completion of March of 2026, which will allow us to start drawing fibers and learn fiber drawing and characterization before we start assembling the quads and testing on dummy quads, how to do the assembly of the quads. So this is a quad assembly. The last assembly essentially is a monolithic assembly, which consists of the penultimate mass and the actual test mass hanging by fused silica fibers. And so the two critical technologies are the fiber drawing and the fused silica ear tap bonding. And towards this, colleagues from the LIGO project have been spending time at Glasgow University at Professor Giles Hammond's lab, learning both fiber drawing and ear tap bonding. And they plan to be back. So this will be a phased program. We have the initial set of visits, which got completed recently. They'll be revisiting in July of next year and follow it up in September of next year again to complete this. By which time we'll have our facility for the fiber drawing and ear-tap bonding trials at the testing and training facility of LIGO-India, so that we are able to continuously train people to do this when we require for the LIGO observatory. The other facility that is set up and running at the testing and training facility is a 10-meter prototype. Currently, the control systems is what we are focusing on. So the mirrors are mounted on flexures and they are being aligned remotely, and the controls people are working on it. We have developed a small laser system also indigenously. I'll detail that further as we talk about future prospects. And that is just a laser system that's built from scratch for this facility. So all the components for this 10-meter has been built within the country, and the optics and the laser system has been developed within the labs and within the country. And that is essentially to catch up and build the expertise required for system engineering as we move forward on the digital development. So this is a laser system for the front end for the 10-meter prototype. And currently we are in the process of testing the single stage suspension for its installation, which we hope to complete by December. And this is a work in progress. We have built the PMC for this, and this has also been characterized as part of that, essentially to learn how to model, design, fabricate, and develop remote cleaners as part of this activity. The control systems for this is also built identical to what LIGO uses and what we'll be encountering when we build LIGO-India, so that people developing control systems and also training on this facility find similar systems when they go to LIGO-India Observatory for training, for installation and commissioning, and also when they go to LIGO Hanford and LIGO Livingston for training, so that they are not required to learn new mechanisms and new techniques or new designs, and they remain similar. So with these expertise developed and the tenders going ahead, we hope to build the LIGO-India Observatory by late 2030 or by early 31. Probably will slip by 3 quarters or 2 quarters if we don't catch up. Essentially because we had some delays in the EPC tender. But otherwise, we hope to hold schedule by two quarters delay, simply because there's a collaborative project with the LIGO US, and the lessons learned during the installation and commissioning of the 2 LIGO US detectors is what we hope to leverage and have less surprises when we do our installation commissioning because of these lessons learned from the LIGO US. So parallelly, one of the outcomes that we hope LIGO India contributes to the larger community is the bridging of the generational expertise. The LIGO US detectors were built in 1995, and as we interact with them, we see that many of the people who had done the initial design to move on. So we hope that the expertise that we develop in the country and the design and other installation commissioning expertise that we develop kind of carries forward this expertise to the next generation of detectors when the Cosmic Explorer and Instant Telescopes are built in the later part of So one of the upgrades that we need to concomitantly do is the squeezer light development. So this is something that the PSL substream is working on. So they have initially built the second harmonic laser for this pumping the OPO, which builds the squeeze light source. And the prototype squeeze light source also has been developed on the table, and some squeezing up to 5 dB has been demonstrated. We'll be building an engineered prototype of this so that this could be a component that can be tested at the 10 meter. And then subsequently write a project to build the squeezer for the LIGO India, which is something that we hope to arrive in the configuration if we get funded. And this is funding we'll seek from DAE as part of DAE's contribution to the quantum mission in the later part of 26 or early part of 2027. So that construction of this squeezer would happen concomitant with the installation commissioning. So one of the other upgrades that you see on the calendar is what is called A-sharp. And A-sharp essentially is to go to higher powers of the laser. I'll detail how we can probably do that also if we get funded. And also to build a heavier suspension and also improve on the coating. The coating activity is an extremely distributed activity. There are large groups across the world, part of LSE, both abroad and India, who are working on coating thermal noise. And whatever gets finalized, we are hoping that we can get barter effort versus contribution from the LIGO lab to get our mirrors coated, similar to what was done for the CERN. And that could allow us to do some upgrades which are similar to A-hash or A-sharp, as it's called, for our detector also at a later part in the post-LIGO operation phase. So towards this, as I mentioned, even for LIGO-India for training, we had built the laser expertise for the N-Pro amplifiers from scratch. We are able to generate 10, 20 watts of power. Currently, we have a small BNS project with CGCRI to develop low noise fiber amplifiers, which can go up to 100 watt, which will take this 10 watt to 100 watt. This is at the background. As I said, for the LIGO-India, all the components for the laser are being contributed for the LIGO-US. But to build expertise, and also if we have to build the laser for the AA Sharp, we need to build the required expertise within the country. So if the 100-watt laser, which is due to be completed in a year's time by CGCRI, is successful, then we can do coherent combination of those 100-watt lasers to build a 500-watt laser similar to what is required for the A-sharp application. The other expertise that's required is the heavy suspension. So we have done the optic suspension developed from scratch with simple test benches, Fabry-Perot's, suspension for the 10 meter. And currently, some of our team members are at, some of the LIGO-India team members are at Glasgow University developing a 3-stage suspension from scratch, both for the 10 meter at Glasgow and 10 meter Aracat, which also builds the expertise for the suspension development. Initial work was done on a fiber drawing system with components that was available to us. Currently, we are building this fiber drawing system. I would like to note here that the fiber drawing system is being developed, which can draw fibers up to 2 meters, what will be required for the heavy suspension. So that the facility required for development of the heavy suspension is already available. And once activities on the LIGO-India installation is translated to commissioning efforts, some of the system engineering teams can start working on this to see if we can build capacity for A-hash upgrades if we get funded in the future part. Something similar is being also done for the optics, and we were able to seek funding from DAE for scaling up our optics fabrication facility. The optics in LIGO is exquisitely flat. It's like lambda by 1000, which is not routinely what vendors in India or abroad can manufacture. There are hardly 1 or 2 manufacturers. I think Zygo is one of them, and that's what LIGO US uses. So we thought that this would be a good reason to build this expertise in the country. We have been able to build optics for the 10 meter up to 6 inches, up to lambda by 1000. And this is currently what we are scaling up, both in terms of metrology, an 18-inch measurement facility for characterizing the optics. And recently we completed the fabrication facility building, and this allows us to build substrates for some of the future detector upgrades if required. But it hinges on the coating being still done by LMA or whoever is LIGO's partner in way of bartering either manpower or expertise for any future activities that we can contribute to the LIGO project and get coatings done. Beyond that, probably LIGO Voyager is not on the schedule, but if silicon optics is used and cryogenic developments are done, this is something that we plan to do on the 10 meter as the initial expertise building. We have the capacity to do silicon polishing up to 6 inch currently in the center, which we can scale up to 500 mm once the advanced facility is there. So some work on this to kind of build expertise if required, if LIGO Voyager ever becomes funded, ever becomes a reality as an intermediate step to Cosmic Explorer. We would like to see if we can contribute some components or our detector could be upgraded in that facility. And ISIS coatings, there's some groups in India also working, including TIFR Hyderabad and Aracat. And this will be a global upgrade in the sense that whatever coatings LIGO US implements, we'll try to see if the same can be done by the same vendor for our optics also. So we're not focusing on the facility buildup at the coatings at this point, probably focusing on the substrates part. Some distractions from the LIGO part, which is some parallel activities about building half-meter telescopes, a project which we call Dragonfly informally at this point. And we are trying to see if we can build a telescope less than $500 million with building the imager and everything in-house, so that we can have a few array of them and stitch this data together to build a large data set, which can probably be used for searching kilonovas. And there's interest in other applications like near-Earth objects and other things also, so that can get this funded. But this will be a smaller funding. But we are trying to build as part of the 500 mm telescope, 500 mm optics scale-up. We're also building capacity for lightweighted mirrors and also CCD readout as part of the GetGo project, so that the cost and the fabrication effort for the telescope can be left small. And we intend to prototype this and transfer this technology to the Indian industry, so that if this project gets funded, it's more of a buy and install kind of an effort. One other project that looms on the horizon is the space-based decihertz detector. The academic community has been putting together the science requirement for this, so that LIGO-India and probably a interferometer in space can form a multi-band detector in the future. There's some preliminary design and analysis activity for the optical system for this. One of the things that benefits from the capacity builder for LIGO-India is the large aperture optics. We'll require beam expanders if we have to build a simple LIGO in space, and that current capacity and expertise that we're building in optics and instrumentation, once LIGO-India is completed, probably could help bolster the required expertise for these kind of activities, like large aperture interferometers. So stop here, and if there's some questions, I can try to handle them and answer some of those questions.
Thanks, Sandil, for a very nice talk. So what we can have few questions related to the talk right now, and later on in the panel discussion, we can have more general questions. Any questions? Okay, I think I saw Ajith first. So.
On a very thank you, Sandil, for this update. A very mundane question to start with. So this building design is very different from the LIGO US, right? Is this intentional to make it different to meet?
Yes, so it partly is driven by what we can do in India. For example, in US, concrete buildings are controlled by zoning laws and also recoveries and other things. And also, so they have their own rules in terms of how buildings are constructed in the US. In India, all large projects are usually permanent buildings. Civil buildings are usually concrete buildings. Though at LIGO, at the training and testing facility, we built a hybrid one where the building is concrete, but the roofing is a steel structure similar to what the LIGO US built. That we built because of speed, though we did not take advantage of the speed because of COVID. The civil construction was chosen because something that's easily implementable in India. However, the specifications in terms of temperature stability, in terms of floor vibration, in terms of acoustic resonances and final floor noise is identical to what is specified for LIGO US observatory also.
So you don't expect to have any surprises?
Hopefully not. In fact, I think at least my personal belief is that because of the heavier construction and we may have some advantages compared to steel structures which can resonate at acoustic frequencies. So,
okay, thanks.
It's more of the expertise that's available in the industry. As I said, in India, most of the observatory or most of the construction of large natures are concrete based. And
so, yeah. So the next is about the telescope, the Dragonfly. So even if there is a good argument for making a telescope, wouldn't be a seriously limited with a site. So
no. So this was just a kind of a background activity. This is a small project that we have with IIT Indore. It may not be at the site. It may be at the site in simple sense that that's the logic we're using, that we have enough space along the arms. And if we can make these as modular components with pods, they can be pre-installed here. It might happen that the LIGO-India observatory is not the best place for the viewing. It could be at Hanley or other places. But you have to have a starting point to start putting together the prototyping. That's the point. This is very early on. Nothing serious has happened other than prototyping a telescope and trying to do technology transfer for it. So that in the scale of 2030, we have a vendor who can readily provide us half-meter telescopes of low cost.
Okay, thanks.
Hi, Sandil. This is Sukant.
Hi, Sukant.
Very good to see this progress.
Is that a comment?
No, it's okay. Okay, thanks. And also the various collaborations gaining momentum, like the suspension fiber drawing with Glasgow, the optical fibers with CGCRI, and of course LIGO US also remains engaged on multiple fronts. I wanted to hear if there are other critical areas where maybe additional collaborations would benefit, and also how should one get in touch with the LIGO-India project if somebody identifies an idea and would like to collaborate?
So this is a kind of a double-edged problem, because whenever we go to our funding agency, the first focus is to get LIGO-India construction as the highest priority. For example, even the Dragonfly project is something that happens in the background, and that is a very low key priority compared to what is required for LIGO-India. The Get-Go project got funded because we were able to make the case that suspensions are something that we need to really build expertise on. So if something similar is there, for example, control systems, that is one other expertise that we need to have good collaboration so that people can be trained on multiple fronts. Another thing that's picking off, and that probably we may have to do concomitant with the LIGO lab, is machine learning and AI, which is something there's a lot of interest in the academic institutions also, and there's a lot of push at the 40-meter also. The holy grail of the LIGO detectors would be to do remote operation using MI, artificial intelligence, but that's to build a digital twin and things. So that is one area which can directly benefit the project where collaborations are welcome. So if we have proposals where we can show that this can directly enhance the schedule of LIGO-India or the sensitivity of LIGO-India or the construction phase of the LIGO-India or the utility of LIGO-India, I think it'll be easier to put through collaborations easily. So that is something that we are also trying to do with the Australian group for the laser part, so that some of the expertise in laser and squeezing can happen there without burdening the LIGO labs, because LIGO labs is also hosting a lot of training program from LIGO-India. So that is one area. The immediate expertise would be the squeezer to build the LIGO-India squeezer. And the other one is, as I mentioned, the AI/ML, apart from other global things like coatings and coating noise reduction, which is anyway across the spectrum.
That helps. Thank you, Senil.
Thank you for the very nice and comprehensive talk. I have a very simple question. Maybe you have already answered it. So it's regarding the sensitivity. When the LIGO-India is online on 2030 or 31, how would you compare the sensitivity?
The plan is to arrive as an A+ configuration with something like 35 watt. Instead of pushing on the laser power, we hope to push on the squeezing part so that we arrive with a sensitivity of something like 100 megaparsec plus in the late 2030 or early 2031. That's the target for the project at least.
Yes, but how would you compare with the other two LIGOs in the US?
So currently the other two detectors are operating at something routinely at 150, 160 megaparsec routinely. And I think by the time we are operational, this may be 200 plus. So the one of the advantages we have because of the lag is that the lessons learned or the expertise learned in LIGO lab, if our detector is identical, can be readily translated to our detector also. So though we start at 100 megaparsec, there's a potential that if we are meticulous in our installation and commissioning, can quickly scale up and starting to match the sensitivities of the other two observing observatories. Yeah.
Okay, that answers my question. So we will be able to somehow catch up with the other two LIGOs.
Yes. Yeah. So this is the collaborative effort because this is a joint effort by both LIGO Lab and LIGO-India. And so we are building a detector which is almost similar to the Hanford detector and our Livingston detector. And we hope that all the problems that were encountered, both installation and commissioning, can be avoided in India. But still, we'll discover new problems. But with joint expertise, we hope to have a faster commissioning to this sensitivity and also faster reach to the detector sensitivity of what the other two detectors have. We are hoping that by the time we are online, coatings issues get solved out and we go closer to 300 megaparsecs or higher, which is the target for the Asia.
Just to add one comment here is that when the I think Lalit and all have shown that even if LIGO-India comes online at half the sensitivity, it will be still extremely useful for source localization. Just to give an example, the Vargo detector, when GW17 weight 17 was detected, had 1/4 of Hanford's sensitivity in terms of horizon distance and 1/2 of Livingston's sensitivity in terms of that. But that was good enough to reduce the error circle by 1/6, factor of 1/6. Okay. So even if LIGO-India sensitivity is low, it should not be in the beginning, it should not be a problem.
Actually, I think you've answered my question. I was going to ask exactly about this, the same question that was asked about sensitivity. Just a comment here. I'm delighted to see the progress here. I mean, from the social point of view, I think LIGO-India is in fantastic shape right now. I mean, Indian scientists have been involved in the science here, starting with Sanjeev Durandar and Bala Iyer from the beginning. And it's very clear now that that's very sort of well integrated here into the community. So that's fantastic. Scientifically, though, I do wonder whether it would make sense to be slightly more ambitious and to say that the goal is to match the sensitivity of the LIGO instruments. I accept your point that even at half the sensitivity, you still make a big scientific contribution. But why not aim a little bit higher and say our goal is to make LIGO-India at least as sensitive as the two US detectors? That would be great.
Sandil, do you want to comment on that?
If you look at the project, so this we are talking of the construction phase of the project. So construction phase of the project, we were a little conservative that we'll have an engineering run, which will essentially show that we can repeatedly lock the interferometer and also have a reasonable sensitivity to shoot for. So that is why this conservative number of 100 megaparsec per second. But as I said, this is not a project that we're doing alone. We're doing this with the LIGO lab. And any expertise that is available for the LIGO lab to bring our commissioning on par with other two observatories is something that LIGO lab would be, or the larger LSC would be helping us do that. And also we'll be having people moving back and forth, learning the required commissioning training expertises. There's a large program in commissioning. IUCAA set up the initial part, the 10 meter, the 40 meter, the two observatories would serve as training part also. And I would claim that the 100 megaparsec is what we're shooting for purely on a conservative front from a project standpoint of view. But if all things go well, the commissioning or the detector improvement can be quite rapid once the observatory is online and operating at this conservative number. And that is, so in a year or two, we can try to see if we can match all three detectors identical, because this detector technology is going to be identical to what we have for LIGO US, except for site-specific differences, either in terms of resonance of the building, 50 hertz versus 60 hertz, things which are something that we are cognizant of now, and things which could be surprises, but maybe mitigated faster because we know how to actually operate these kind of detectors from the experience from the two other detectors. Yeah. So it can be quite more progressive in the sense that like early 2032, 33, we can try to match the operating detector sensitivities if that's the target.
Yeah, if I can just add a quick comment. So the attitude that we have for this project in India and in the US is that LIGO-India will be a LIGO laboratory. And if you look at the global network, there's a really good chance that LIGO-India will quickly become one of the most sensitive, if not the most sensitive detector. And it also, from the next generation report that the so-called Caligari report, LIGO-India also has a future that stretches into the 2040s. So some of these upgrades that Sandil is talking about, like potentially something like Voyager, are very relevant for LIGO-India. Whereas if Cosmic Explorer gets approved, that will sunset the LIGO laboratories in the US, especially if ET also goes forward. So it's LIGO-India, but the important part of that is that it's LIGO. So in our vision, it'll be LIGO-Hanford, LIGO-Livingston, LIGO-India, where the scientific program, the upgrades, the sharing of knowledge and technology will be done in a uniform way so that they'll all operate. Hopefully at mid-2030s, they would all be operating at close to the same level.
Yeah, so we close the talk now.